properties of limits. This is going to seem kind of strange at first, but I promise once you see some examples, this turns out to be very simple. But we're going to learn what the properties of limits are and then learn how to apply these properties of limits. So if you have your textbook, you can turn to page 57 and see the list of them. There's 5 of them. Theorem 1.2, properties of limits. Now, I have them on the next screen as well, so if you don't have your book, don't worry. But these things may seem really obvious, but they don't hold true for everything in calculus. We're going to be doing something called derivatives pretty soon, and all 5 of these properties do not hold for derivatives. Only 2 of them do. So this really is important to know when you are and when you are not allowed to do these things. So here's what the 5 of them say, and I'm going to try to maybe separate it here so it's a little easier to read. But if you look up top, it tells us that for some value, the limit of function f is going to be called L, and the limit of function g is going to be called K. So what this is saying, for example in the first one, is that if you multiply f by a number, then all that's going to change is you just multiply your limit by a number. So for example, if you have a function and you know the limit at a certain point is 5, well, if you double the function, you've changed the function, but you can take the limit of that new function and it's just going to be double 5, which is 10. Okay, and in number 2, sum and difference, basically it's saying, oh, and actually I should have plus or minus there, either one will work. Let's say you know the limit of one function is 7 and you know the limit of another function is 2. Well, if you create a new function by adding the 2 of them together, f plus g, then the new limit will be 9, 7 plus 2. Same with product. If you choose to make a new function by multiplying 2 things together, then you can just multiply their limits individually together. Same with quotient and with power. If you raise the whole function to a power, you can just raise the original limit to the power as well. Now, like I said, I know this may seem obvious or it may just seem abstract. You'll see how easy these problems really are in just a moment. But just so you know, only number 1 and number 2 apply to derivatives, which we'll do in a little while. We actually have to have very special rules for product, quotient, and exponents, the power at the bottom with derivatives, because these properties don't hold for them. So limits are nice and easy with these. This is really a good thing that makes them easy and straightforward. So here's an example. I just chose 2 functions, f of x being x squared minus 5, and g of x being cosine of 3x. Now, they may or may not actually give you these equations. In fact, they may just give you this second line where they tell you the limit of f is negative 5 and the limit of g is 1. Now notice, both of them are approaching 0, and that's important. You've got to be approaching the same x value for all these. They can't just be a random spot on the function at any point. It's got to be the same point we're approaching. So looking at part A, it says the limit as x approaches 0 of 5 times cosine of 3x. So what I've really done is I've taken this function and I've multiplied it by 5. Well, I knew the limit of just the cosine of 3x part was 1. So I know this is going to head toward 1. So my answer is just going to be 5 times 1, which is 5. It's really that simple. This is basically just a giant substitution game, is all it is. So part B, we know the limit as x approaches 0 to f of x plus g of x. We want to know. Well, we know the limit of g of x individually is 1, and the limit of f of x individually is negative 5. So to solve it, just do 2 times negative 5 plus 1 gives you negative 9. And then C. We know individually the limit of f of x is negative 5. The limit for g is 1. So to find the limit of this new thing where they multiply them together, you just do negative 5 times 1. And finally D, it says the limit as x approaches 0 of f of x cubed. Well, we know f of x by itself had a limit of negative 5. So now for our new function f of x cubed, we just need to do negative 5 cubed, which is negative 125. So when you see these weird things with limits, if you'll just think substitution, it'll be a piece of cake for you. So here's one specific application. These are fairly well-known trig limits. The first one being the limit as x approaches 0 of sine of x over x equals 1, and the limit as x approaches 0 of 1 minus cosine x all over x equals 0. If you need a way to help remember this, I just look at it this way. The I in sine kind of looks like 1, and the O in cosine kind of looks like 0. So if you can just put those things in your brain, that might help you. You do need to memorize this from my class, but only in the sense that if I ask you what the limits are, you know it's either 1 or 0. So you know which is which. That's all you need to know. You don't have to memorize the functions. You just need to be able to recognize them and know their limit when asked. So we're really going to, in these examples, be applying the properties we talked about. Because if you look at the first example, it's 4 times sine of x over x. Well, if I just split this up, this is really 4 times this function right here. And I know the function in parentheses, sine of x over x, has a limit of 1. So if I'm multiplying that by 4, my limit will just be 4. And then on the next example down, we have 7 times 1 minus cosine x over 3x. Well, if you look closely, that's really just 1 minus cosine x over x times 7/3. And we know the part I outlined in green goes to 0. So we just do 7/3 times 0, which is 0. Now the third one gets real creative. If we just split it up, we'll find that these things are actually all very familiar. I'm going to start by taking this 3 and pulling it out as 1/3. Now it's a 1/3 because that 3 is on the bottom. Then I still have x squared on the bottom, but if you think about it, x squared is really just x times x. So what I'm going to do is split this up in 2 and give 1 minus cosine x an x, and give sine of x an x as well. So I know this piece goes to 0, this piece goes to 1, and I can just do 1/3 times 0 times 1, which is of course just 0. Final example here, we have the limit as x approaches 0 of tangent x. So here's one thing I want to try to help you think about. The tools we've been given, this is still related to these problems back here. The tools we were given, these two right here, are in terms of sine and cosine. But the problem they're asking us has a tangent. So you need to think, okay, what I know is sine and cosine. And what they're asking me about is tangent. So how can I relate tangent to sine and cosine? Well, if you know your trig identities, you know that tangent is equal to sine of x over cosine of x. And what we really have here now is a fraction, sine of x over cosine x, divided by another fraction, x over 1. And whenever you divide fractions, you simply multiply by the reciprocal. Okay, well hopefully it's starting to show up. You start to see what the pattern here is. If you remember, when you multiply, it doesn't matter what order you multiply in. So I'm going to swap the order of these two. I'm going to make it sine of x over x times 1 over cosine x, and take the limit as x approaches 0. Well, this one I now recognize. Sine of x over x has a limit of 1. And this piece over here I don't recognize, but I can use direct substitution. If you look back at the two rules I have, you can't use direct substitution because there's an x in the bottom. But here, if I plug in 0 for x, cosine of 0 is 1, so this also goes to 1, and that is the answer. 1 times 1 is 1.